Hello friends, I welcome you all in the class of physical chemistry. We have already started the new chapter, nuclear chemistry. In previous lecture, already discussed about the introductory part of the nuclear chemistry, classification, subatomic particles, nuclear stability, radioactivity, types of radioactive decay, discovery of radioactivity, and general characteristic of radioactive sample or substances. Now, in this lecture, we will discuss the decay kinetics or kinetics of radioactivity reactions. All the radioactivity decay or reactions are spontaneous, and all decay reactions are obeys first order chemical kinetics. Radioactive sample, consider a radioactive sample contain n0 number of atoms initially present and n number of atoms present at time t. Then according to the chemical kinetics, the rate of radioactive decay or reactions at any instant is proportional to the number of radioactive atoms present at that time or instant. So the we can write in equation form, rate is equal to minus dn upon dt is proportional to the number of atoms present at that instant. So we can rewrite minus dn upon dt is equal to lambda into n, where lambda is the proportionality constant, or we called as decay constant or rate constant of the radioactive reaction. N is the number of atoms present at that instant, minus dn upon dt is the rate of radioactive reaction. The radioactive decay constant or rate constant is expressed in time inverse, minute inverse or second inverse. That means unit of the first order chemical kinetics or radioactive decay is time inverse. Let us see the derivation of rate equation for the radioactive reaction. So integrate the rate equation between the limits, that is dn minus dn upon dt is equal to lambda into n. For integration purpose, for integration purpose, similar type of terms in one side and other will be the other side. So minus dn upon n, integration lower limit n0 to upper limit n is equal to integration of lambda into dt. So lambda must be out of integration sign because it is constant. So we can rewrite integration of minus dn upon n between the limit n0 to n is equal to lambda, then integration into dt. lower limit 0, upper limit is t. So after integration of this is minus ln n. So substitute the value of upper limit minus value of lower limit. So substitute upper limit, that is minus ln n, minus minus will be plus. So plus ln n0 is equal to lambda upper limit t, lower limit 0, then t minus 0. So we'll take the ln common. So ln n0 upon n is equal to lambda into t. We have interested in the here decay constant, that is lambda. So decay constant lambda is equal to 1 upon t ln n0 upon n. So we can also rewrite the equation in the logarithm form. Lambda is equal to 2.303 upon t log of n0 upon n. So this is integrated form of rate equation for radioactive reaction. So we can determine the decay constant if we know the number of atom initially present, number of atom at time t. From this equation we can able to determine the rate constant for radioactive reaction or decay constant. If we know the decay constant and number of atoms present at present and initially, then we can able to determine the t. That means at that time the number of atom will be decay by this decay rate lambda. From this derivation we can also derive the exponential form of rate equation. If we rewrite this equation, it is in the form of, that is reverse form, ln n upon n0 is equal to minus lambda t. So if we take the antilog on both sides, so antilog and ln will be cancelled, so n upon n0, and antilog of RHS side will be the e raised to minus lambda t. So n upon n0 is equal to e raised to lambda t. Then n is equal to n0 into e raised to minus lambda t. If we know the lambda t n0, so we can able to determine the n, that is number of radioactive atom present at that instant. So this is exponential form of the rate equation for radioactive reaction. So next will be the half-life period. So half-life period of the radioactive reaction is defined as, that is time required to decay half of the initial number of atom or initial concentration. It is denoted by T1 half. For that we know the rate equation, integrated form of rate equation, or lambda is equal to 2.303 upon t log of n0 upon n. At half life, t will be the t1 half and n is equal to n0 upon 2, that means half of initial concentration. So substitute the values in above equation. Lambda is equal to 2.303 upon t1 half log of n0 upon n0 divided by 2. So this n0 will cancel out. So we can write the equation. Lambda is equal to 2.303 upon t1 log of 2. We know the log of 2, that is 0.3010. So substitute the value of log 2. We get lambda is equal to 0.693 upon t1 half. Here we have interested in t1 half, that is half life. So this will be go LHS side and this will go to this RHS side. So T1 half, that is half life, is equal to 0.693 upon lambda. So if we know the decay constant, then we can able to determine the half life period of the element. If we know the half life period, from this equation we can able to determine the decay constant or rate constant for this radioactive element. For example, so uranium 238 having half life 4.51 into 10 raised to 8 years. Then Tn 232 half life will be 1.39 into 10 raised to 10 year. Radium 226 half life is equal to 1.62 into 10 raised to 3 years. So this is some of the example. Next point is the unit of the radioactivity. The first unit is Curie. The most common unit of the radioactivity is Curie. Before 1948, Curie was defined as rate of disintegration of 1 gram of radium 226, because Marie Curie has discovered the radioactive element first, that is mineral form of radium 226. So they have worked with this radium 226 and try to find out the rate of disintegration. So this definition was modified, that means amount of radioactive substance which will disintegrate at the rate of 3.7 into 10 raised to 10 disintegration per second. So 1 gram of the radium 226 will be having disintegration rate 3.7 into 10 raised to 10 disintegration per second. So they coin the unit of this radioactivity, that is 1 Curie is equal to 3.7 into 10 raised to 10 disintegration per second. So we can also millicurie or microcurie 10 raised to minus 3, Curie 10 raised to minus 3 or 10 raised to minus 6 if it is in micro. So second unit for the radioactivity is becquerel. So this is SI unit of the radioactivity. It is defined as the activity due to the 1 disintegration per second. That is 1 becquerel is equal to 1 disintegration per second. So 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. So that is interconversion of 1 Curie and becquerel. So 1 becquerel, that means 1 disintegration per second, but Curie will be the 3.7 into 10 raised to 10 disintegration per second. So 1 Curie is equal to 3.7 into 10 raised to 10 becquerel. So this is about unit of the radioactivity. Here we stop the lecture. In next lecture we will see the application part of the radioactivity or radioactive element. Thank you.